to you, Scott.
Yep, thank you. Yes, I just want to thank the chairs and the technical group for the opportunity to give this talk about a topic that Richard and I find really interesting. Richard, did pass on his sincere apologies for not making it today. We did have this system set up where we were going to swap 4 times during this talk, which would have been good to try out, but unfortunately we can't do that. But hopefully you won't know where we will swap if I do a good job. So hopefully all slides will be equally well presented. So this talk is about sediment transport and scour in the ocean environment. It talks about knowledge and future directions as of 2 years ago. There's been a few changes since, and I'll talk about them in the final slide. But a theme that's going to come through this talk is going to be the importance of field data, field observations. They're really driving knowledge in sediment transport and scour in a couple of ways. They're identifying processes that we didn't know existed or we didn't expect, and that's leading to or motivating more research. And field observations are also a great way to validate what we do in the lab. So to kick off the talk, I thought I'd start with the latter example where it's arguably probably one of the best examples I can think of where we've used field observations to validate a model. And once we do that, we can then use that model to extrapolate forward in time and optimise design. So this is the field example I'm going to touch on. We've got this subsea structure. It's a midline connector structure for an oil and gas development, but what it does is not really important. From a scour perspective, what's important is the fact that it's a geometrically complex structure. It's porous, you can see through it. It's a circular mud mat, and on top of that is a structure that's roughly cuboidal in shape. You can see around the bottom here we've got a skirt. The skirt's about 600 millimetres deep, and the diameter of the mud mat is about 8 metres. It's orientated as shown in the top left here, so you can see these 2 circular parts of the structure here. They're sort of facing west, approximately west, as it's deployed on the seabed. So what do observations look like for this type of structure? Well, the main form of observation that we have is ROV video footage, but quite good video footage. It's quite systematic, quite close, and quite well focused on the structure. So I'm going to take you on a bit of a trip around the circumference. We're going to start where this blue dot is, and you can see here the seabed is where I've drawn the sort of blue dashed line. So there's a scour, or there's an exposure of the skirt there of about 300 mil or so, just under 300 mil. So relative to the diameter of the structure, on this sort of polar plot, we're at about 3.5% of the diameter. As we move around with the ROV, we move to this sort of southerly part, and you can see scour depth's got a little bit bigger here. And as we continue to move around, we see the scour depth getting bigger again. On this sort of northeastern edge, we get the deepest scour depth. Here we're getting to a scour depth of about 500 mil, so there's only 100 mil left before we would undermine this skirt. And that's one of the reasons why this data was sort of provided to us at this point, was the question of whether we would undermine and what could be done to mitigate. And then as you continue to move around the structure, the scour depth then reduces, and as you get to the back, we actually have no scour at all. So a really interesting, cool scour pattern around this structure. We know the structure is not uniform, it's not axisymmetric, and neither is the scour profile. So what we can do here is we can go into the lab and we can see if we can reproduce this type of distinct scour pattern. And to do that, we really need to match 3 things. We need to match the structure, the fluid mechanics, or the fluid properties, the hydrodynamics, if you like, and we also have to match the soil conditions or the erodibility of the sediment. So in terms of model testing, with 3D printing, it becomes really easy to capture these type of complex subsea structures. So this is the 3D version on the bottom you can see here. We actually did this at a few different scales. I think this scale I'm showing you here is probably at about 1:20 scale, or maybe 1:30 actually, this orange one. And the metocean conditions for this site were almost perfect, right? So this is a directional histogram of the nearbed seabed currents, measured at about 1.5 metres above the seabed. This is a year's worth of data. And you can see that almost all of the significant currents come from the southeast, so sort of from this sort of direction here. And The histogram also bins in terms of what we call flow intensity. So that's the flow velocity divided by the critical flow velocity required to cause the sediment to move in the free field. We obviously get scour occurring when we get a flow intensity above 1, but we can also get scour occurring when the flow intensity is less than 1 because the structure itself accelerates the flow locally just due to its presence. So if we have a look at that's the polar plot I showed you before, and that's that reference current direction. So we've got the structure geometry, we've got the flow conditions, and we can mimic them in a flume really easily as a unidirectional flow, which is fantastic. The final thing we need to do is match the sediment properties. And we had some soil samples from this particular site. We were able to use the sediment in the lab that was a little bit different, but not too different. And we were able to run flow conditions to match the flow intensities we observed in the field. And as a result of that, this is a scan profile from the model scale experiment, where you can see the scour pattern here. Obviously, blue colours are scour depressions, red colours are sort of, if you like, deposition locations. And if we run around the perimeter of this model structure and we sort of plot it on top of the observations, you can see that we match a number of aspects of the scour profile we see in the field. We definitely match some of the asymmetry we can see in the field. We match the extent of the scour. Some of what we miss, I think, is because of the fact that we've simplified the mid-ocean down to a single current direction. But otherwise, this is an ideal scenario where we've got a model scale experiment now that's capturing a number of the aspects we see in the field. And later in the talk, we'll come back to this example and I'll show you how we can utilise this model to make some better design choices. Okay, so the talk today is going to cover these different aspects. I'm going to start just with a very quick review of sediment transport and scour, just touching on a few basic things. I think many of you will be familiar with those, but we've included them just for completeness. We'll then talk a little bit about available field observations, and we'll put down a couple of requests for the future, hopefully. We'll also talk about advances in laboratory testing. There's sort of 3 themes there we'll touch on. And then the exciting part is the case studies. I'll share some case studies and then some conclusions. Like I said, the case studies here are going to focus on not everything that's probably important going forwards, but we'll hopefully highlight some of the things that we think are important. Things that we're not going to talk about today are scour mitigation, unfortunately, and we're also not going to talk about the interaction between global scour and local scour, but they've become topics that are becoming quite important at the moment and going forwards. Okay, so in terms of sediment transport, there's all sorts of things that we're interested in. We're interested in how sediment moves, whether it moves along the bed in bed load or whether it gets suspended and moves as suspended load. But arguably, probably the most important thing about sediment transport is the distinction between what we would call non-cohesive sediment and then sediment that's fine and appears to have some apparent cohesion. So what I've got shown on the right here is a plot of grain diameter, median grain diameter on the horizontal axis against threshold shear stress. Now that is the shear stress that the fluid is applying to the bed, so it's a force per unit area that the fluid applies as it moves. As the flow velocity increases, the shear stress that's applied to the bed will increase. The black data here is a database from predominantly from the North Sea and around Europe, and then the blue dots here are actually data we've got from doing testing on samples recovered from the northwest shelf of Australia. And these blue dots are all cases where we have pretty limited fines content, and we find that the blue dots pretty much follow that black dashed line. That black dashed line is a famous line. It's called the Shields curve in sediment transport. It basically tells us that the shear stress scales with the weight of the particles, which are proportional to the or scale with the grain size. Obviously, if we then go to sort of a silty sand, as shown on the sort of middle, one across from the left there, silty sand tends to have more fines content, and what we find is we get a significant increase in erosion resistance, and that's a really important point, something that we will touch on again in a case study later on. At the moment, there's no, consensus about a model that can predict the increased erosion resistance that we see for fine-grained sediments. So a lot of work relies on taking samples and doing erosion testing in the lab to understand that erosion resistance and then use that going forwards for design purposes. And we're not just interested in the threshold shear stress, we're also interested in how quickly the sediment moves when we exceed that shear stress, and so we can get things like erosion rates out of the similar, out of model testing, out of element testing, if you like. And there's just some examples there. The red line is for that silty sand, and the blue is for the superfine sand on the left, which is a silica sand. Okay, so that's I guess the basic thing about sediment transport. And then scour, there's two canonical structures that we look at for scour in the literature. There's a lot of work on these. One is a pile, vertical pile. Some classic flow structures illustrated there that are important in driving the scour process. There's the horseshoe vortex, which is called a horseshoe vortex because when you look at it in plan view, it wraps around the front of the pile and then separates off the back, so it looks like a horseshoe in plan. That's responsible for lifting sediment and mobilising sediment at the front side of the pile. We have streaming around the edges of the pile, just due to the blockage that the pile provides, and we have vortex shedding in the wake. All those different flow features can elevate the shear stress locally and move sediment, and we get these scour holes resulting, like many of you be aware of. Typically on the upstream side, we would have a relatively steep side to the scour hole. Usually that's seen to be around the angle of repose for the sediment, and in the lee wake we tend to get a shallower sloped scour hole. The horizontal extent of these holes are on the order of 50-60 metres for wind turbine monopiles, so pretty big holes, massive amounts of sediment being moved. And just quickly to show you what this looks like in the lab flow, here is coming from the left. If you look carefully, you'll see some avalanching on the front edge of the scour hole to the left, and what's most noticeable here is the ejection, if you like, of sediment upwards at the back behind the pile, and then that sediment is depositing about a diameter behind the pile, causing a sedimentation mound. That sedimentation mound and that suspension of sediment in the lee wake is quite sensitive to the sediment grain size and the flow intensity. But the scour pattern in front of the hole is actually not that sensitive to the sediment type. For a pipeline, we have a slightly different set of flow structures. We have what we call a luff vortex in front, which causes a little scour gutter to often form in front of pipes, and then we have this separation across the top, and we get this large lee wake vortex that's in the vertical plane. With pipelines, we sort of have this, alternate outcome depending on the initial embedment of the pipeline. If the pipeline and the embedment here, many are familiar with, but the embedment would be the adjacent point of the sediment relative to the bottom of the pipe. If we have a large embedment, we don't get scour occurring. We end up getting sedimentation. This lee wake will often drive a build-up of sediment behind. But if we have an embedment that's lower, we'll get scour occurring underneath, and we have these scour holes that will grow under the pipe and along the pipe, and eventually may lead to lowering. So I just got a quick video there to show you, if you haven't seen, what this looks like in an experiment, the scour process. And this is just being driven by the fact that the flow accelerates under the pile, again due to the presence of under the pipe, due to the presence of the pipe, and that causes erosion to occur. Right, so that's the basics. Now for a subsea structure, it's somewhere in between these two. So streaming is still important for a subsea structure, as too can be the horseshoe vortex. The aspect ratio of the structure will influence whether we get lee wake vortices in the vertical or the horizontal plane. But as a first approximation, if you can imagine somewhere in between those two is a more standard generalised structure. Okay, so what field observations are currently available, and what would we use in scour assessment, scour prediction? They're mainly around the sediment, the seabed, and the wave and current conditions. So on the far left, we've got a picture here of the geophysical data that we might receive. Multi-beam surveys are becoming more and more common and becoming more and more resolved and more accurate, and they're fantastic at determining the morphology of the seabed. If you have concurrent or successive scans, you can work out things like bed form migration really accurately. mobile layer thickness as well can be linked back to geophysical data. And these are obviously important for bigger picture questions like, for example, if we wanted to develop in a particular area, maybe we could influence where structures would be placed to avoid interaction between large-scale bed forms and the structure itself. Sediment data in the middle is also really important, as typically from a scour perspective, we're interested in the sediment at the very surface. And like I said before, erosion testing is often required for any sediment that's not a simple sand. So that's very useful. I've got a point there about the geotechnical parameters and the fact that CPT can be useful. I know this is a question from Richard, really a challenge from Richard. So CPT is often considered to be a little bit debatable in the top metre or so from a geotechnical perspective, but CPTs do still record something, and that may be related to the sediment erosion properties or the sediment properties generally. So that's something that he's keen to continue to work on going forwards, about the value you can extract from that from the perspective of sediment transport. So samples are really, really crucial. And then lastly, we've got wave current conditions and also water level linked to that. So time series measurements are really important. Resolution is key. We need the time resolution to be sufficient to obviously capture waves, if waves are important. So we need to be at a lower resolution in the wave period. Maybe we need to be even lower in some senses where we think turbulence is important. Turbulence can influence sediment transport rates. It can also influence the responsive structures too. So that is becoming important. But the key takeaway here is, and this is important, sort of a request, I guess, in terms of field observation, is that often when we work on a particular problem, the geophysical data, and in particular the mid-ocean data, is gathered before, during the design phase, before structures are placed. Structures will then be placed and there might be monitoring, and there might then be observations of scour. But unfortunately, during the period of scouring, the mid-ocean or the current and wave measurement has stopped. So concurrent measurement of local flow conditions together with surveys is going to be significantly useful. And if that could be done going forward, then both Rich and I think that would be a fantastic, would lead to a fantastic outcome in terms of understanding scour processes. Okay, so just quickly, advances in laboratory testing. There's three interesting ones to touch on. One is that we're seeing lab facilities getting bigger and bigger and bigger, especially in China, but also in other places too. So what you can see in the top row here is some model scale experiments in the fast flow facility at HR Wallingford. There's a structure to the left, is a sort of a protection structure for a pipeline at 1:20 scale. There's a jacket structure at 1:30 scale in the middle. On the right-hand side, there's a pile that's actually at 1:2 scale. And this is exploiting symmetry by chopping the pile in half and sticking against the wall of the flume. The movement to larger and larger facilities is all about this need to try and mimic more closely field conditions. So if you can avoid scale effects associated with very small models, you can get better insight into the scour process. The other thing we're seeing, and this is a plug really for UWA, is facilities that are really aiming to reproduce the near-bed current conditions that are important. So the O-tube is an enclosed flume that we have at UWA, and if you want to know more, you can definitely ask me about this tonight or tomorrow. It allows us, because it's an enclosed flume, we can do oscillatory flows that are quite fast and have quite variable period, which is difficult to do with an open-top wave flume. And we can do things like mimic cyclones. So there's a cyclonic time series there of near-bed velocity. And we can look at things like pipe stability, but we can also look at all sorts of things on the seabed in those type of conditions. So that's one trend. The second trend is all about better modelling sediment properties in the lab. If you have a sand, things are relatively straightforward, and I won't spend too long going through that flowchart on the left here, but for a sand, essentially what we need to do is make sure we capture the mobility in the model scale experiment. That includes understanding amplification from the structures that might be placed on the seabed, but also includes understanding when we're getting what we call clear water scour and live bed scour. So live bed is when the entire seabed is mobile, and clear water is when we're just mobilising sediment local to the structure due to amplification. So as long as we go through that flowchart, we have a pretty good idea, we think, and we've got plenty of validation to show that for simple sands we're fine. We can do reasonably good experiments. There's a caveat there around suspended sediment, but typically do very well for sands. Where there's the challenge is with these finer materials, and what I've shown on the right there is actually a carbonate fine sediment, 80 micron, I think this example is. So this exhibits an erosion property off the Shields curve. And this is an example where we've done at the top there is an erosion test, and at the bottom is a model scale experiment around an object. A lot more of that work needs to be done to understand how to relate erosion rate to scour rate. And unless we can do that, we need to do things like actually model the sediment in the experiment. So that's the second thing, modelling sediments more accurately. And the third thing is laboratory techniques and capabilities. These are always improving in all different areas of lab testing. There's a host of different materials there. Different equipment there. I'm not going to focus in on all of it. But one thing I think is particularly cool, which we've been doing a lot at UWA lately, is using this thing called Mesh Room. If you haven't heard of that, definitely Google that. It's basically just using a series of photographs that you can take on an iPhone, put it into software, and it gives you a 3D image really well. There might be opportunities to do this with ROV footage. We're not sure. It's something we're exploring. But it's definitely revolutionised the way we do experiments. Okay, so case studies. That time down there, that's my time. Is that right? Okay. No one's hungry, so that's all right. No. So case studies, most important, exciting part. So we're going to start with sedimentation of cables and pipelines. We're going to look at this pipeline, and for some of you this will be particularly, you'll remember this pipeline and know it well. So it's a 0.64 metre diameter pipeline. It's orientated off the northwest shelf of Australia. It runs in the offshore direction. It's 26 kilometres long, and there's variable soil and mid-ocean conditions along its length. This is a plot of the water depth, the top plot there, water depth against KP, so distance along the pipeline. You can see at KP0 we're in deep water, 800 metres, and as we go along the pipeline we go into shallower water, eventually getting to depths of about 100 metres or so. And what you have below that is two plots of embedment. The first one is the midfield embedment, which is sort of illustrated on the top right figure here. So it's a location 3D away from the centre of the pipe. And then a local embedment, which is just 1D away. And you can see some interesting trends here in both the midfield and the local embedment. In the deep water region, both of them are quite high and don't change much in time. The different colours here are different surveys. In the shallow water region, both of them are quite low and don't change much in time. Where it's interesting is in the middle here, where we have a reasonably low midfield embedment that doesn't vary much in time, but we have a local embedment that increases significantly in time. And this coincides with an area where we have relatively sandy sediment, and we have internal wave events that can cause intermittent flow perpendicular to the pipeline from either direction. So if we draw some sections through this, section A is in that deep water region, B and C are in this interesting region, and D is in the shallower region where we don't see much change. And if you look at those in profile view, so A, B, C and D, you can see with B and C we're getting this build-up of sediment that's giving us this local embedment, and in the midfield we've got not much change. A, we've basically got a deeply embedded pipe all the time, and D, we've got very little happening at all. So this is an example where we looked at this field data and we were thinking, okay, well, that's not actually something that anybody's reported in scour experiments before. It's not really scour, it's sedimentation, but it's definitely happening in the field, so can we explain it? And the way we did that was to look at the mid-ocean data and try and mimic in the lab the type of flow conditions, those internal wave events, and see if we could create profiles that looked similar. So this here is just a video that's had the speed increased, and what we're doing here is we're randomly producing currents from either direction that last for a certain duration. They're random because the internal waves that are measured in the field are actually random. They're not always in the same direction. So the internal waves in this region predominantly run along the pipe, but there's not any internal braking waves that cause these perpendicular currents. So you can see over the course of that experiment we've built up these berms. And when you look at them, this at the top here is looking at them at a very small model scale, 40 mil pipe, and the bottom is 150 mil pipe in a large O tube. We get self-similarity of those berm shapes. The left is just plotting them on top of each other for slightly different conditions. And these match the field conditions really, really well. And we can do things in the lab now, which we have done, where we can, for example, work out how quickly these berms occur for a given set of flow conditions. And that can be important for understanding, for example, pipeline response when you might first turn the pipe on. You need to know what the local embedment will be at that point in time. So using this type of research, we can predict what the embedment might be for a pipeline placed in the field. So this is an example, first case study is an example where we've used field data to motivate experiments that have provided insight into the processes of sedimentation, and in turn that then feeds back into design. So case 2 is the scour of subsea structures with mud mats. We'll come back to this skirted foundation. And I said that now that we've got a validated model, we can use this in design. So one way we can use it is to look at the propensity for scour. And the way we measure that is in terms of what we call an amplification factor, which is shown on the vertical axis here. This is how much the shear stress is increased local to the structure compared to what it would be in the free field. Okay, if you have a big amplification factor, it's very easy to get scour with a very small flow because it's amplified, the shear stress is amplified so much near the structure. So we can see, I just want you to draw your eye to these circles here, which is the full structure. We also pulled this structure apart and tested different parts, but if you just look at the circles here, you can see that depending on the direction in which the flow is approaching the structure, which is captured by this parameter beta, we get differences in amplification. So there are certain directions which are good, give us minimal amplification, and certain directions which give us quite large amplification, so like 0 and 90 degrees here. And beta is defined so that 0 degrees would be normal to the edge of this sort of cuboidal superstructure. So why is this important for design? Well, this by itself isn't, unless we thought we could vary the structural geometry. So we could alter the structure. This is showing us the effect of the geometry of the structure on the potential for scour. This is the same type of test, but where we've stopped the structure from being porous, so it's no longer porous. You can see what the effect of geometric porosity is on scour potential. And then lastly, and this is the most important one, is we can actually look at how much scour protection or what region around the structure we'd need to protect to stop scour happening. And we're varying here the diameter of the region protected, and we're able to determine what is the optimum extent of scour protection to mitigate scour for this structure. So given that we've got confidence in the model, doing that type of work in the lab, the confidence continues and we can come up with an optimal design solution. So in this case, the model is validated with field data that can be used to inform mitigation and future design. I'm probably going to go through this one pretty quickly. I have to go through everything pretty quickly now. So this is another type of subsea structure. This is now combining the pipe we saw in the first case study with the subsea structure in the second. We've now got the two together. And this is a protection structure that's protecting this, this spur here on top of the pipeline. And I'll play this video for you. This is sped up 60 times. This is testing in the fast flow facility at HR Wallingford. And what's interesting here, if you look at the front corner of the structure, you can see the red start to appear. That's the skirt being exposed. And what's even more interesting is if you look at the pipeline just behind that skirt, we're actually undermining that pipe just here. So the presence of the structure is actually causing scour initiation along the pipeline. And that's this particular structure is based on a real structure that might be used in the field, obviously. Here's some other pictures, and I think these are also a good indirect indication of how well model testing can capture the field, because if you look at those profiles in plan, you wouldn't know if that's a model or field data. This is actually a model scale experiment scan result. This particular slide just shows the effect of increasing sediment mobility through increasing flow intensity. You can see we're getting more rippled bed features, more scouring around the object. The effect of flow direction, and what happens if you separate the pipe and the structure. And clearly that separation is important because we just saw interaction between the two in that video where the presence of the structure was causing undermining. And so the takeaway from this case study is that skirts can be undermined by scour, and this is critically controlled by sediment mobility and flow angle. And these are things that we would need to measure very reliably in the field to understand if this model is accurate. Okay, the last one is, I've got 15 seconds. Is it okay if I go over by a minute? Yeah, okay. Up to 5, okay, yeah, thanks. So the last one's probably the most relevant, most interesting. So offshore monopiles. So this is a fantastic figure. On the vertical axis is the scour depth normalised by pile diameter, and on the horizontal axis is the water depth over pile diameter. And this is data from the field. This is from a number of offshore wind farms listed there in the legend. There's a blue horizontal line in this figure, which is the DMV, recommended value for scour around a pile, 1.3D, taken at face value. And then the red line there is actually a scour prediction model developed called OptiPile, developed by HR Wallingford. That has a higher scour prediction for large water depth of about 1.7D, and then tapers off as the water depth gets smaller. That's an effect that's well known in scour literature. As you reduce the water depth, you reduce the strength of the horseshoe vortex and reduce scour. So that tapering off of the red line is due to that process. But what's interesting here is to look at the different data, because obviously having a very good prediction of scour depth around a pile is important for design. And it's great to look at all this data that's been compiled and try and understand whether that is in agreement with these predictions. So we start off with the sandy sites. So we've just circled a bunch of data there which corresponds to Scroby sands. And this was arguably the first set of data that was available for analysis. And interestingly, it's all just below, pretty much all below that blue dashed line, which was great news at the time. This was acquired about 2 or 3 years after the monopiles were installed. And in following this, they were scour protected. So there's no data beyond this point. So that's where things end for the Scroby sands data set. Then there was some additional data here for Arklow Bank, just one data point, also well below that blue dashed line. And then we have a whole heap of data here that came in for Robin Rig. And this data set is quite spread and goes above the blue line. We have data points that are quite low. The thing about the Robin Rig data set is it's not all from 2 to 3 years after installation. Some of it's quite, I think even the multi-beam was taken just after installation, and then some of the other data is taken in the order of 2 to 3 years afterwards. So a lot of the variability here is the fact that we're just observing scour in the field at the time of survey. We don't know where we are in terms of the time development of that scour process. The red line and the blue line I should have outlined, they're predictions of maximum scour depth under a sustained current. So I guess what we can conclude from this is the Scroby sands data, although it was below the blue line, was probably sampled a bit too early on in the lifetime of that project to actually get an idea of what the maximum scour depth could have been. So it gives you an idea, and this just touches on the point of being able to properly understand the scour process to work out whether these field observations are actually giving you an indication of what you're looking for, in this case the maximum scour depth. There is other data here, so there's cases where we have more complex soil conditions, so veneer of sand over clay. In this case here, the idea would be that the clay layer beneath is less erodible and is curtailing the scour depth. There's cases here where they're in predominantly clays. This is Kentish Flats. I think this is London clay, Richard was telling me. And then we've got cases where there's silt present, which is also influencing the scour process. So the takeaway point from this figure is we've got a bunch of field data in different soil conditions, and as a result we're getting very different scour depths. And what that points to is the importance of the erosion properties in driving the scour depth. And that's probably an obvious thing, but great to see that come through with this type of data set. So it's just 2 slides to finish. If we focus in on the clay influence, this next slide is a busy slide, but it's made up of, it's focusing on sediment here that's quite resistant, so it's fine sediment. And if you look on the right-hand side, it's made up of two types of data. One is lab data. There's a lot of lab data available on different sediment types, including fine-grained sediments. And it's also, on the bottom right, you can see pulling in data from field observations. And what's been plotted here is on the vertical axis, we've got the scour depth normalised by the diameter again. And on the vertical axis, we've actually got the undrained shear strength of the soil. Now, unless you're very good at picking up patterns and keys really quickly, all of the model data is pretty much over here. So in the model scale data, we get a range of scour depths. But what's important is that very little model data is actually at high undrained shear strength. And the reason for that, most likely, is because nobody wants to do an experiment on a sediment with a very high undrained shear strength that doesn't scour very quickly or at all. So most of the experiments are in, a lot softer, I guess a lot lower strength soils. Whereas the field data goes right out into these large undrained shear strengths. So the puzzle here is the fact that we get this data in the field that's not overlapping everywhere with model data. And in the field we have very high undrained shear strengths, but we still do have scour holes occurring, right? So that's a bit of a surprise. We would expect for such high undrained shear strength we'd have almost no scour. So the question is, what is causing that scour process? And you can see in the bottom figure here, you can see a depression around this pile. This is in a clay-like material, field data. So you see this depression that looks like a scour hole. You can also see the footprints from the installation jack-up. But you can see a scour hole here. Now this wouldn't be something that we think we could predict using ideas just in terms of standard scour prediction. We don't think this material would be erodible enough to cause that hole. So the hypothesis, and this is Richard's hypothesis, which I think is a good one. It's not proven, but it's hopefully something that can be motivating for future research. What we've got here is we've got an interesting plot, and we'll follow first of all these open circles. These are for a low strength soil, something that we're used to, like a sand or maybe a slightly silty sand. And what we have here is, first of all, the importance of hydraulic erosion on the scour process. And for these type of sediments, that's really important because it causes a lot of sediment mobility and scouring. Pile installation, the idea here is this has a low relative importance on the local soil profile around the pile because maybe it's easy to get the pile into those type of soils. And then as you come up here to thinking about the in-service cyclic lateral loading, maybe as the pile moves backwards and forwards, it can cause some gap erosion, but that will probably be small relative to the hydraulic erosion just due to the presence of the pile itself. Whereas for the high-strength soils, those ones that had the really high undrained shear strength, hydraulic erosion is probably not that important. In fact, we wouldn't think it would cause much scour. So the idea is it might be pile installation effects or in-service lateral loading, cyclic lateral loading, that's actually causing, through mechanical interaction, this local depression of the sediment that we see around the pile. So this is an area for future research, but it's an area that would be good to think about going forwards. Either way, the takeaway from this last case study is that Scour Offshore expected to be controlled by sediment mobility and mechanical effects with response related to soil conditions. All right, so I've pretty much finished. So conclusions are here. They also take a while to talk through, so I won't talk through them. But essentially there's two sets there, knowledge conclusions and conclusions about the future. The knowledge really is that we're able to do useful design when we've got validated models based on field observations. In the future, we need to continue to rely on things like laboratory testing of soil cores. We need to be able to account for things like structural complexity and perhaps mechanical cyclic effects on the sediment. And if we can continue to do appropriate scaled laboratory testing in tandem with things like CFD, which are becoming more and more practical, then we're going to get in a position where we can make good predictions going forwards. So that's it. Thank you.